A DDR5 memory module sits on the bench. The label identifies it as a product of domestic Chinese supply, and by the standards of any ordinary product description, that label is accurate. The module was assembled in China, packaged in China, and fabricated at a Chinese facility. We are going to open it layer by layer, from the edge connector to the cell array, and the thing we find at the bottom is not what the surface implies. The outer layers confirm the domestic story. The deepest layer complicates it in a way the documentation does not mention. The cuts run from outside to inside. First the module level assembly, then the die and its bond architecture, then the controller and its process node, then the cell array where lithography becomes visible in the silicon, and finally the lithography step itself, which is where the dependency lives. The module on the bench is a standard dual inline memory module form factor carrying a row of black DRAM packages on each face, a register chip near one edge, and a gold finger edge connector along the bottom. At this outermost layer, the localization story is strong. The printed circuit board substrate is domestic work. The solder joints are domestic work. The edge connector, the package housings, the capacitors and resistors mounted at the board level. All of these represent genuine Chinese industrial capability operating at volume. Chinese suppliers, including those in the supply network associated with Changxin Memory Technologies, have demonstrated sustained competence in substrate fabrication, package assembly, and board manufacturing. The company's production figures, as reported in domestic industry publications, indicate that DDR5 output at this layer has reached meaningful commercial scale. This layer exists because assembling tested dies into a shipping module is a distinct industrial capability from manufacturing the dies themselves. Countries routinely build strong assembly operations before they build strong fabrication operations because the barrier to entry is lower and the equipment is more accessible. The outer shell reaches the market first. It generates the headline production numbers. It is also, structurally, the layer with the lowest dependency on restricted capital equipment, which is why it localized first. Nothing at this layer requires imported tools that are subject to current export controls. The module's assembly tier is, in the precise sense, sovereign. Moving one layer inward means removing the package and examining the DRAM die itself. Changxin Memory Technologies is the principal Chinese company producing DRAM at domestic fabs, and the company has publicly stated progress toward DDR5 class product. Analysts tracking Chinese semiconductor output broadly characterize the company as operating at what might be described as a mature but not leading-edge node for DRAM, though independent confirmation of the exact node generation from published laboratory measurement is limited. What the teardown suggests, from the die dimensions, the cell density, and the package configuration, is a cell array consistent with architectures that deep ultraviolet lithography can print rather than the more compressed geometries that require extreme ultraviolet tools. The die inside this module is, by the available evidence, a domestically fabricated DRAM die. That is a genuine and recent industrial achievement. Chinese fabs have produced working DRAM at commercial quality and in commercial volume within roughly a decade of serious investment. The cell structure inside this package is Chinese silicon, processed in a Chinese facility by a Chinese workforce. The bond architecture visible when the package lid is removed reflects both the process node and the packaging toolset in use. For the node range Changxin appears to be working at, wire bond and conventional molded packaging remain entirely viable approaches. This is not a constraint unique to the company. It reflects where the technology roadmap sits relative to the most advanced global competitors. Samsung and SK Hynix have moved toward more advanced through silicon connection architectures for their highest density products, but those architectures are tied to finer process nodes that require different tooling. The packaging tier on this module is matched to the die it contains. One layer further inward sits the controller die, which is the component that translates signals from the memory bus into the address and timing operations the cell array requires. DDR5 modules at this configuration carry a register chip that handles some of those functions, and in more complex server-class configurations there are additional buffer components. The logic die that performs these functions is a distinct fabrication target from the memory array itself, and it matters to the localization story because a module whose memory array is domestic, but whose controller is foreign, is a partially localized product. That is not a criticism, it is an accounting. Independent teardown reporting on Chinese DDR5 modules has not uniformly confirmed the provenance of every logic die across the range of products now shipping. Some controller components in the broader market for Chinese DDR5 may be sourced from fabs outside China. On this specific module, the controller die is smaller and visually distinct from the memory dies, and its package markings, where legible, do not resolve the question of fab origin without additional analytical steps beyond optical inspection. The teardown can identify the die. It cannot certify the fab without electron microscopy and chemical analysis, neither of which is available at the bench level. This layer exists because DRAM cells are passive storage elements. A capacitor holds a charge representing a bit, and a transistor gates access to that charge. Without active logic to address the cells, select rows and columns, apply refresh cycles, and interface with the host system's timing requirements, those cells are inert. The sophistication of the controller affects read latency, error correction strength, and compatibility with the DDR5 specification as implemented in host chipsets. The localization question at this layer is real, and the answer for this module is not fully settled by the physical evidence available here. The next layer inward is the cell array itself, which is where the manufacturing process becomes readable in the silicon. Each DRAM cell is a transistor paired with a capacitor, arranged in a grid whose pitch, the distance between adjacent cells, is the direct physical record of the lithography tool that printed it. Smaller pitch means higher density, lower cost per bit, and more capacity per die. Smaller pitch also means shorter wavelengths of light and more capable lithography tools. At the process nodes Changxin Memory Technologies appears to be working at, the critical dimensions require scanners operating with deep ultraviolet light sources. The leading-edge DRAM producers, Samsung in South Korea, SK Hynix in South Korea, Micron in the United States, have moved or are moving toward extreme ultraviolet lithography for their most advanced nodes, which allows them to print features that deep ultraviolet scanners cannot resolve cleanly at production yield. Changxin, by all available evidence and by the company's own public communications, is working with deep ultraviolet tooling, which places its current production capability at a node range that is viable and commercially meaningful while remaining behind the frontier. The cell array in this module carries within its geometry a permanent record of the tools that made it. The pitch is measurable. The pitch implies a wavelength. The wavelength implies a class of scanner. This is not inference, it is physics. The constraint is not located in a policy document or a trade filing. It is located in the silicon, in the spacing between transistors, in the feature dimensions that the available light source could resolve. This brings the dissection to the deepest layer, which is the lithography step itself, and this is where the dependency becomes fully visible. Deep ultraviolet lithography scanners of the kind required to print the features in a DRAM cell array at Changxin's current node are manufactured primarily by ASML in the Netherlands, by Nikon in Japan, and to a lesser extent by Canon, also in Japan. The etch tools and deposition systems that work alongside those scanners in the fab are supplied primarily by Applied Materials and Lam Research in the United States, and by Tokyo Electron in Japan. Export controls imposed by the governments of the United States, the Netherlands, and Japan have restricted or prohibited the transfer of the most advanced of these tools to Chinese semiconductor fabs. The restrictions have been applied in successive rounds, with the most consequential, those covering ASML's extreme ultraviolet systems, in place before Changxin reached its current production level. The deep ultraviolet toolset that Changxin is operating today was largely acquired before the most recent rounds of restrictions took effect. The company's existing installed base of scanners was purchased when purchase was possible. The ability to expand capacity or advance to finer nodes depends on whether additional scanners can be acquired, and that question is currently open in a way that has no straightforward answer. No domestic Chinese lithography tool supplier has demonstrated a production-capable deep ultraviolet scanner meeting the specifications required for leading-edge DRAM manufacturing. The Shanghai Microelectronics Equipment Company is the most visible domestic scanner developer, and its development programs are real and ongoing. The gap between its demonstrated capability and the specification required for DRAM cell array patterning at Changxin's current node remains substantial by the available evidence, though the company does not publish detailed performance data and independent verification is limited. Development timelines are genuinely uncertain. This layer exists because semiconductor lithography equipment is not the kind of system that trade policy makes temporarily difficult to obtain. It is the kind of system that took the existing manufacturers decades to develop, that requires supply chains spanning dozens of countries, and that embodies accumulated optical engineering, precision mechanics, vibration isolation, and laser source development that cannot be replicated quickly from public knowledge. An extreme ultraviolet scanner from ASML contains components sourced from roughly 5,000 suppliers across multiple continents. The lead time from a decision to develop a domestic alternative to a production-capable tool operating at frontier specifications has historically been measured in roughly a decade, even for well-resourced programs starting from an existing technical base. The cell array in this module is domestic because the scanner was imported before the scanner became unavailable. That sequence is not a criticism of the strategy. It was the rational approach. It does mean that the constraint is structural rather than temporary, and that the module contains the evidence for it in its cell pitch. Consider a loaf of bread described as entirely homemade, the flour locally milled, the yeast cultured in the kitchen, the shaping and baking entirely the baker's own work. The oven was manufactured abroad and cannot currently be replaced. The bread is homemade in every sense the word ordinarily implies. Without the oven, there is no bread. The oven leaves no marking on the finished loaf. It is present in every slice. That is the relationship between this module and the scanner that printed its cells. Three things this dissection cannot settle. The first is the precise node generation of Changxin's current production die. The company's public statements describe DDR5 class progress. No independently published laboratory measurement of the cell pitch, with methods described and results verifiable, has confirmed the exact critical dimension. The teardown suggests a node consistent with extended deep ultraviolet capability, but suggests is the honest word, not confirms. The second is the serviceable lifetime of Changxin's existing deep ultraviolet scanner inventory under conditions of restricted access to spare parts, maintenance services, and calibration support from the original equipment manufacturers. Lithography tools require ongoing manufacturer support. The effective operational lifetime of a tool separated from that support chain is a physical question with no publicly available answer for this specific situation. The third is the timeline for domestic Chinese scanner development to close the capability gap. Development programs are real. The incentives distorting both optimistic projections from domestic sources and pessimistic projections from foreign competitors are also real, and both sets of projections should be read with that in mind. What the module shows is the current location of the boundary, not the speed or direction of its movement. Taken as a whole object, this DDR5 module is evidence that China has built a functional domestic DRAM industry at unusual speed, and that the industry has done so by building from the outside in, establishing competence at each layer above the lithography step, while the lithography step itself was supplied by foreign capital equipment acquired before the restrictions tightened. The outer shell is domestic. The packaging is domestic. The fab is in China, the workers are Chinese, the company is Chinese-owned, and the die is Chinese silicon. The machine that printed the critical features in that silicon is Dutch or Japanese in origin. That fact does not reduce what has been accomplished. It does require that the word domestic be given a precise definition, and the honest definition runs out at the lithography step. The observation that matters most here is not about geopolitics in the abstract, it is about what the module's documentation omits. The spec sheet lists timing parameters, voltage rails, and capacity. It does not list the lithography tool. That omission is itself a piece of data. The layer most exposed to foreign dependency is the layer the documentation treats as invisible. The localization gradient, high at assembly, lower at packaging, lower still at lithography, is not accidental. It reflects a deliberate build sequence, growing capability from the outside in, which means the inside remains the most foreign part. And the speed of that outward to inward progression is not in dispute. What the layers reveal is that speed and completeness are different measurements, and that the remaining foreign-dependent distance, while not long in absolute terms, is load-bearing in structural terms. A supply disruption at the assembly tier would be a production problem. A supply disruption at the lithography tier would be an existential one. The restriction that current policy is most actively trying to enforce against this module is not visible on its surface. It is visible in the cell pitch. The sovereignty the module represents is genuine at every layer the teardown reaches before it reaches that one. What the module proves in the end is that a supply chain can be sovereign everywhere except where it is most foundational, and that the most foundational layer is precisely the one that leaves no marking on the finished product. There is another object worth opening: the domestic lithography scanner that Chinese fabs are developing to replace the foreign tools this module depended on. If you want to see that dissection next, name it in the comments. If this kind of layer-by-layer examination is what you come here for, subscribe so the next one reaches you when it publishes.